Well, hello, everyone. Welcome to the VaNTAGE Seminar. And today we're continuing our series of talks on fundamental groups and arithmetic applications. And for our first talk today, we're very happy to have Shun Ishii, who's going to be speaking about the Galois action on pro-P fundamental groups of punctured CM elliptic curves. And Shun, is it all right if we record this talk?
Yes, please.
Wonderful. And please, audience, please feel free to ask questions during the talk. Okay, Shun, go ahead.
Thank you so much for the introduction, and I would like to thank the organizers for giving me these opportunities. And so today I would like to talk about the Galois action, the property fundamental group of punctured elliptic curves, and this talk is based on the following two papers, and which are based on my thesis. And my main motivation of these studies is to understand the Galois action on the non-abelian fundamental groups of punctured elliptic curves, so more explicitly. Uh, so there are some classical studies where the hyperbolic curves is P1 minus 3 points, and today we I present our recent attempt to extend some classical results to genus one case. So first let me start with some notations, and let K be a number field. So in most cases we assume that K is Q, or imaginary quadratic fields of class number one. And so we fix an algebraic closure K bar of K, and we also fix an embedding K bar into the field of complex number C. And let Kx be a smooth curve over K. And we mostly consider the case where X is hyperbolic. So what is hyperbolic? So hyperbolic means that the associated Riemann surface is uniformized by the upper half plane, and more group theoretic way to rephrase the hyperbolicity is that the topological fundamental group with some base point is not abelian. For example, I think the most simplest example of hyperbolic curves is a P1 minus 3 points. And in this case, the topological fundamental group is just a free group of rank 2. And I think the next simple example is once punctured elliptic curve. So here E is an elliptic curve, and O is its origin. So we consider a open uh, subset of E obtained by removing its origin. So in this case, we also have in this case, the topological fundamental group is also isomorphic to the free group rank 2. And for more higher genus cases, we obtain the surface group, and and oh, sorry, and so we need some more notations, and let xk bar be the base change of x to the algebraic closure k bar. And we in this talk we let pi 1x denote the ether fundamental group of x with some base points, and pi 1x k bar is a geometric ether fundamental group of x. And we in this talk we consider the Galois action on the geometric fundamental group of x, right? So before defining the Galois action on the fundamental groups, we recall two facts, and the first is a comparison between topological fundamental group and ether fundamental groups. So in fact, the geometric data fundamental group is known to be isomorphic to the profinite completion of the ether fundamental group. So this justifies the name geometric fundamental groups. And the second one is the ether homotopy exact sequence, and it uh, is the following exact sequence. Uh, so in this, so pi 1 xk bar and pi 1 x and gk. So gk is the ether fundamental group of the spectrum of K, and this is isomorphic to the absolute Galois group, which we denote by GK. And we also consider the propy version of outer Galois action. So let pi 1 xk bar p be its maximal propy quotient of the geometric fundamental group. And now, so we obtain the following continuous homomorphism. So by the homotopy sequence above, and we obtain the following continuous homomorphism from the absolute Galois group of K to the outer automorphism group of the geometric fundamental groups, which is defined to be the quotient of continuous automorphism group modulo the inner automorphism group. So basically, if we have an element of the absolute Galois groups, then we it uh, lift it to the ether fundamental group of pi 1 x, then such a lift acts on the geometric fundamental group by conjugation. So such a lift is unique. So up to an element of pi 1 as a geometric fundamental group. So this action defines the outer action, not the action, the outer action, the geometric fundamental group. And this outer Galois representation also induces the following propy outer Galois representation from the absolute Galois group of K to the continuous outer automorphism group of the propy geometric fundamental group. So in this talk, we mainly consider the second one, the propy outer Galois representation. And so when X is not hyperbolic, then we can easily describe the outer Galois action as follows. So in the case of P1 or A1, so then the geometric fundamental group is trivial. So rho X is also trivial. And if X is the multiplicative group, multiplicative group in ZM, then phi 1 xk bar is isomorphic to the profinite completion of Z hat, and then we obtain the cyclotomic character. And in this final example, let E be an elliptic curve over K, then the geometric fundamental group is isomorphic to the product of the periodic Tate module, so this adelic Tate module, and then we obtain the usual Galois representation associated to the adelic Tate module, right? So however, when X is hyperbolic, so in, when X is hyperbolic, so this outer representation is extensively studied in the context of Arnaverian geometry. And one famous theorem says that if X is, so this is a theorem by Berry and Voevodsky and Matsumoto, Hoshimochizuki, and the theorem says that if X is hyperbolic, then rho X is injective. So the absolute Galois group is entirely contained in the outer isomorphism group of surface group, profinite completion of surface group. And so this theorem is first proved when X is P1 minus 3 point by Berry, and then once punctured hyperbolic curves by Voevodsky, and when X is affine, it is proved by Matsumoto, and finally, in general cases, it was proved by Hoshimochizuki by using some non-trivial techniques of combinatorial, so-called combinatorial Arnaverian geometry. And when so let me so what about rho xp? So rho x is known to be injective by the previous theorem. So in this slide, we consider the case, we consider the propy outer Galois representation. And then we have some easy arithmetic. We obtain some easy arithmetic constraints on this representation. The first one is a group theoretic one. So the first this lemma, so the first statement is that the outer automorphism of the propy outer the propy geometric fundamental group has an open propy subgroup. So this is almost propy. So hence, so this implies that the image is also almost propy, and the kernel of rho xp is very big, so very large. And the second one is arithmetic constraints. And so if V is a prime of k above, lying above some prime which is not equal to p, at which x has good reaction. So then rho xp is unramified at V. So the image of an inner subgroup is trivial. So, and we remark that the converse also holds by, so in some sense that a non-Arvinian analog of Neron-Shafarevich criterion still holds, which is proved by Oda and Tamagawa. And, and here is a brief sketch of the proof. So the first statement follows from the fact that the kernel of, so the subgroup consisting of outer automorphism which trivially acts on its flattening quotient is propy. So this is a brief sketch of the first statement, and the second follows from the specialization isomorphism for pi1. So, and so these are two easy constraints, and so the one natural question is more there, there are more restrictions or constraints, and or can we determine the fixed field corresponding the kernel completely in field theoretic or arithmetic terms, right? And so let me introduce the previous result when x is p1 minus 3 points. And in this case, so Sharifi proves the following remarkable theorem and under certain assumptions. So recall rho p1 minus 3 point p is the outer propigal representation. And in this case, let us write so the kanji yama to be the kernel of the fixed field, and let 10 be the maximal propy extension of Q mu P unramified outside P. So this is compatible. This notation is, I think, compatible with Chris's talk last week. And the result, so we have, so by the previous lemma, we have that Yama is contained in 10, the field 10. And all the classical question of Anderson Ihara posed in 1988, I think, is that is Yama equal to 10, in fact. And Sharifi proves the following result. So assume that P is odd and regular prime, and Dreen, so at a certain conjecture of Dreen, which is nowadays often called the Dreen-Ihara conjecture, holds for P. So I will explain this conjecture later. Then, so assuming these two conditions, then we have these equalities, in fact. And so, in fact, now we don't need to understand what the what Drin's conjecture is, since this is already fully solved by works of Hein, Matsumoto, and Brown. So they prove Drin conjecture for every prime speed. So in summary, if P is odd regular primes, then in fact this Yama field Yama is equal to 10. So and 10 is by defined by easy constraints in the previous slide. So this theorem says there are no more restrictions. And the main result of one of the main result of this talk is that analogs of Shari field result for once punctured elliptic curves. And and so let me prepare some more notations. And so let P be a prime which is greater than or equal to 5, and K an imaginary quadratic field which we assume that which has a class number 1, and let E over K be an elliptic curve with Cm. So we assume that the complexity multiplication is defined by the base field K, and let X be the hyperbolic curves obtained by removing uh, the the origin from E. So so this X is called once punctured CM elliptic curves. And Rex P with associated property of the Galois representation, and rho EP with the periodic representation, the usual periodic representation of E. And before proceeding, I will explain my results. So let me observe the following consequences of the theory of complex multiplication. So if we consider the kernel of this the periodic representation attached to E, then we obtain the following decomposition. So this fixed field can be decomposed into two as a composite of two fields. The first one is a field corresponding to the obtained by adjoining all Peterson point of E to K. And the second one denotes which we denote Kp to the infinite power, uh, and it where this means that the Laplace field of K of conductor P to the infinite power. So this is just a maximal abelian extension of K unramified outside P. So this, in particular, the field does not depend on choices of E, although the first factor does depend on. And right, and my main, so here is a statement of main result, and we follow the notation from the previous slide, and we assume the following four conditions. And the first one is that the prime P, which is greater, so which we assume that P is greater than or equal to 5, and it splits in our imaginary quadratic field K as split into two distinct prime as P equal P, the product of P and P bar. And the second assumption is that the class number of the Laplace field K P of conductor P does not divide P. So this assumption is similar to the previous result, and as an assumption of the previous result. And the third one is a little bit technical, but there is a unique prime of the Laplace field of K of conductor P squared above P bar. So this is a little bit technical, but so, and the last assumption is that an analog of Dirichlet conjecture holds, and I will explain in the next section what what an analog of Dirichlet conjecture is. And then the conclusion is that we can characterize the kernel of the fixed field of the kernel completely. So the fixed field is equal to the composite of two fields, and the first one is just the previous one, and the second one is a maximal pro P extension of the Laplace field Kp of conductor P, which is unramified outside P. Right, and this gives in some sense, this gives a non-abelian variant of the classical equality, that we have mentioned in the previous slide. And this direction of inclusion always holds, but the hard part is the converse direction. And so we have some remarks regarding the four assumptions, and let us let us call this equality of between two fields dagger. And the first one is that we compute some examples of pairs KP satisfying the first three assumptions. And in fact, the most hard part is to compute the class number. So, and and the red number means that we use DRH to compute the class number uh, in reasonable times. And second remark is that second remark is about this equality. So we expect that the equality dagger still holds when P even when P does not split in K. So we expect that this holds for all P, which is greater than 5. And for example, we can prove that without assuming any assumptions from 1 to 4, that equality holds when Kp is equal to Q square root minus 3 and 3. And, in fact, in this case, we can reduce our theorem result to previous result of Sharify. And so this is a very special case. And the third remark is that third remark is about the condition 3, so which is a technical part. And so this condition is equivalent to saying that, so if we choose a generator pi bar or p bar, so we can choose it because we assume that the class number is equal to 1. And then this element generates this quotient. So this cyclic group. So, and I think this condition is similar to Artin's primitive root conjecture, and I don't know whether there are infinitely many primes satisfying this condition 3. But for example, so I believe that there are infinitely many, and for example, when k is q square root minus 1, then there are many, so about 35% of primes satisfying this condition. So, and I believe that there are infinitely many primes satisfying all four assumptions, but the most hard part is, I think, the second condition, so the condition on the class number. So this second condition is very strong because it implies the usual regularity of prime. So if the class number Kp does not divide P, then the class number of the P cyclotomic fields also does not divide P. So it's extremely hard to prove the infinitudes. So this is the end of the introduction section. So in the following, we explain what Turing conjecture is, or Turing-Ihara's conjecture is. So to explain the Turing-Ihara's conjecture, and sorry, to explain Turing-Ihara's conjecture, so we need to introduce the weight fit relation on Galois groups. So what is it? So first, let us abbreviate the property geometric fundamental groups as large pi, and let pi m be its descending central series. And then the weight fit relation is defined by this property. So FMGQ is defined to be the subgroup of GQ, which trivially acts on the Propy fundamental groups modulo the m plus 1 the m plus 1 part of degree m plus 1 part of the descending central series. And it is easy to check that this is if a descending central filtration, this is a descending central filtration, and its intersection is precisely the kernel of the property outer Galois representation. And since it is descending central, so we can form the associated graded algebra. So let M be the mth graded quotient of this filtration, and let G03 be its direct sum. And then, so we can show that each graded quotient, so m's graded component is a finite direct sum of m state twists for each m, a positive integer m. So it justifies the name, so weight filtration. So and we can also, since filtration is descending and central, so the sum G3 naturally has the structure of the graded Lie algebra over ZP, right? And the and Dringhardt's conjecture predicts that this graded Lie algebra is in fact free and generated by certain elements. So it states that, so it is proved by Hein, Matsumoto, and Brown, and it states that the Lie algebra, so we take a tensor product with QP, is as a as a as a graded Lie algebra over QP freely generated by certain elements sigma 3, sigma 5, sigma 7 dots in each odd degree, which is greater than 1. And more precisely, so Hein and Matsumoto first proves the generation portion of the conjecture. So this Lie algebra is generated by sigma 3, sigma 5, and so on. And then, so, and later, about 10 years later, so Brown proved a certain motivic version of Berry's injectivity theorem, which I explained before. And so this theorem can be formulated in terms of the category of mixed state motive over Z, which I cannot explain here. And then, so this theorem implies a freeness portion. And yeah, so this is Dringhardt's conjecture. And so the next question is what are sigma 3, sigma 5, sigma 7? And this element is chosen to satisfy the following property. So there are some natural characters called the M3 character, which we denote by kappa m. So this is a character from the m squared component to the m state twist. And so each element sigma m is chosen to satisfy the following property. So that image of and that M3 character generates this image of and the image of M3 character. And so by this property, so sigma m is often called M3 element, the M3 element. Sorry, this is typo. And I we do not explain what three characters are here, but so there are some important properties of three characters. So the first one is that they very naturally arise from the Galois action on the propy meta-abelian, not abelian quotient of pi 1. Uh, so if we consider the abelian quotient, we just get what we get is just a p-adic cyclotomic character, but we consider the Galois action on the propy meta-abelian quotient of pi 1, then there are some pioneering work of Anderson, Ihara, and Coleman, and and Ihara shows that they arise from the three character naturally arise from the Galois action on the fundamental group. And the second property is that kappa m is non-trivial, so for every odd m, and m which is greater than or equal to 3, and this is highly non-trivial. And the last one is the relation between the three character and the arithmetic of sclerotomic fields. And the last one is I forgot to mention that kappa m is can be defined on the level of the f1. So, and if we restrict this character to the fmzq, then it factors through the m squared component. And then if we consider the kappa m from f1 zq, then it is surjective for every odd m if and only if the Van de Waals conjecture holds, so the maximal real cyclotomic subfield of Q mu P has class number prime to P. And so this shows that in some sense Galois action of the Galois action on the non-abelian fundamental groups are deeply related to the arithmetic of cyclotomic fields. And okay, and so let us briefly sketch the Sharpey's strategy of the proof of his theorem. So let x be the p minus 3 points and p and odd regular primes. So his theorem states that these two fields, Yama and 10, are equal. So, so let us briefly give the strategy of his proof. So the first technical but the most important part which we cannot explain here is that so construct nice lifts of three elements sigma 3 or sigma 5. So this is defined to be this is an element of graded quotient. So first we construct nice lift sigma 3 to f3zq and sigma 5 to f5zq and dot dot. And such that the image freely generate this Galois group. So this is the most important part. And then so the rest of part is relatively easy, and we just compare the following two filtrations on the Galois group. So the first one is induced weight filtration. So this has a property that uh, first its intersection is equal to this field, Galois group, this group Galois group 10 over Galois group of 10 over Yama, and the second filtration is a universal filtration of F, so which we denote by Fm tilde. So it is defined by the defined to be the fastest descending central filtration on the Galois group, satisfying that sigma m is contained in Fm tilde for every odd m. And then so we just compare the two filtrations by comparing these graded real algebra. So it's so universal filtration having property. So they have two properties, and the first one is its intersection is trivial, and the second one is the associated graded algebra over ZP is freely generated by three elements. And then we compare these two graded algebra, and then we can conclude that these two filtrations in fact coincide. So, and then by seeing the intersection, so the intersection of the Galois group, weight filtration is the Galois group equal to the Galois group of 10 over Yama, and as was regarding the universal filtration, its intersection is trivial. So we can conclude that 10 coincides with Yama as desired. So this is a very rough sketches of the proof, and our proof also follows this strategy. So first, we assume that the associated graded E algebra is freely generated by certain elements, and then show that the T filtration on the conserved Galois groups coincide. So we basically follow this strategy. And however, so there this approach comes with some difficulties. So the most fundamental question or difficulty is that what are analog of three characters or linear conjecture. So this is a main topic in the following. We answer this question in the following. And and second, uh, difficulty is that so which we omitted in this, which we omit in this talk. So is that in our situation, the structure of the graded quotient becomes more and more complicated. So it's not just the finite direct sum of Tetsuis. So and this causes some problems. So and some parts of the previous strategy do not work. So and to overcome this point, so we introduce the certain two variable refinement of the weight filtration. So which I cannot explain here, and we need to establish some fundamental properties of this filtration. So this is the most technical part. And the last difficulty is that we need to use some arithmetic assumptions on prime p to control the structure of the Galois group of the maximum property extension of kp and outside p. So in the previous case, the Galois group of 10 over q mu p is in fact free and generated by p plus 1 over 2 elements. And in our case, so in our situation, the group is, so we know the number of generator of the Galois group, and we know that there is a single relation, and so so in particular, we have to treat non-free propy group, so which is not, and we have to describe so this relation explicitly to some extent. So, and these are main difficulties to overcome or to generalize the previous approach. And and so now, so we formulate an analog of Drini-Harad conjecture for one-punctured CMD curves. So let us recall the notation. And the difference is that so we assume that prime p splits in k into two distinct primes. So we assume this condition. And also, so we also use the symbol pi, large pi, to denote the propy geometric fundamental group of xk bar. So, and the definition of the weight filtration is the same as the previous case. And we just define FMGK to be the subgroup of GK consisting of outer automorphisms which act trivially on this quotient, and then we can take its graded quotient and the associated Lie algebra, and we want to understand the structure of the Lie algebra GX, and in the so since we assume that P splits, so we have two characters corresponding to the periodic and the periodic Tate modules, which is ZP module of rank 1. So we obtain the corresponding two characters. And using these two characters, we can describe the structure of the graded quotient as follows. And the first lemma is due to Nakamura. So we have that he proves that the GRU MZK vanishes whenever M is odd, and also he proves that GRU2 also vanishes. And this is proved by the fact that the multiplication of -1 induces an automorphism of pi, and this commutes with the Galois action. And we know the Galois module structure of GRU MZK. We take the tensor product over QP, and this is just a direct sum of one dimension, so representations QP M1, M2, and for some integers R M1, M2. So here QP M1, M2 is just a twist of QP by these characters. So So this provides a certain two variable variant of the Tet twist. And in fact, if mi is equal to m2, this is just a Tet twist. And so, and as for regarding analog of Sure characters for each even each even integer m, so Nakamura and constructed a certain homomorphism from so which we denote by kappa m2 plus 2x, and this is a homomorphism from the m plus 2 part of the graded quotient, m plus 2 graded quotient to the symmetric product of the periodic Tate module tensor with ZP1. So he naturally constructed such a homomorphism from the Galois action on the meta-abelian pi 1. So, and it has very nice properties and application. So it has also some application to Abelian geometry. And but the most important problem is that so its non-triviality is not known except for a very special M. So recall that the Sure characters are already not always non-trivial, but in our situation this is not known. So the non-triviality is not known. And in our situation, so the right-hand side can be decomposed. So the target of this homomorphism can be decomposed as into the direct product of one-dimensional representation. So according to this decomposition, so we obtain the family of characters which we denote kappa m1 plus 1, m2 plus 1. So we naturally obtain a two-dimensional, two variable version of Sure characters. And the basic idea is that so use these characters as an analog of Sure characters, right? And so recall that so Sure characters satisfies some nice properties. So it is non-trivial and its surjectivity is related to Van Diverse conjecture. So and in our case, so we similarly we have so many important properties regarding this two variable version of characters. So first one is a vanishing result. So about vanishing of this character. So kappa m1 plus 1, m2 plus 2 vanishes if m1 is not congruent to m2 modulo the order of the unit group of OK. So and this also follows from the fact that the automorphism of uh, automorphism induced by the multiplication by minus 1 is minus 1 or the an element of OK cross commute with the Galois action. So commute with ZK. And if M1 is congruent to M2 modulo the order of OK, then we have this non-vanishing result under a certain condition which we explain in the next slide. And the last one is connect the surjectivity, is related to surjectivity of these characters. So, and first, if the class number of the P class field of K does not divide P, and there is a unique prime of K pair of P bar, then this two-dimensional character, so this also can be extended to F1GK, and this is surjective unless some special cases. And the important point here is the converse also holds. So the properties of characters which naturally arising from the meta-abelian pi1, Galois action meta-abelian pi1 is deeply related to the arithmetic property of imaginary quadratic fields. So, and three remarks is, so one is that the Nakamura so originally Nakamura uh, considers the once punctured elliptic curves over general number fields, and however our proof of this theorem use elliptic units, so and its relation to these characters, and so which cannot be unfortunately which cannot be generalized to non-CM cases. And the third So what is certain assumption? So this is the finiteness of the second cohomology group of the p integer, the spectrum of p integers of OK. So with coefficient in this one-dimensional representation. And this is very hard, and this is in fact a special case of a conjecture of Janssen, I think. And this finiteness is known to hold if mi is equal to m2. So this is a case of Ted twist, and or some special congruence holds. So, and of course there are some conditions on p. So if p is regular in the sense of Wingberg, so the finiteness is also known to hold for every possible indexes. Uh, but in general, this is still open, so we do not know whether this cohomology group is in fact finite. And now we formulate an analog of Trini-Ihara's conjecture. So now we define some index sets. So let I be some index set which consists of two non-negative integers which satisfy this congruence. So this is an analog of the positive even numbers in the case of p minus 3 points. And so assume that this character is non-trivial. So if we have the finiteness of H2, so this is satisfied. And this is also satisfied. The one remark is that this is also satisfied under assumptions of the main result. And choose that some analog of Sure element in this isotypic component of GUR M1 plus M2 plus 2 part of the Lie algebra, and such that the image is under the elliptic analog of Sure character, Nakamura's character is non-zero. So then we formulate an analog of Trini-Ihara's conjecture. So the statement is that this is in fact, freely generated by these elements. And for example, when the order of the class number, order of the unit group was equal to 2, then this conjecture asks whether if this Lie algebra is fully Lie algebra generated by first start sigma 3, 1, and then sigma 2, 2, and sigma 1, 3, and so on. And we have some evidences supporting this conjecture, so which we explain in the next slide. And we have two remarks. And first, if the conjecture holds, we have an explicit formula for the dimension of the greatest part of the algebra. And this is, for example, if the group 4 has dimensions 3 and group 6 and 5 and 8, 10 and so on. So we have an explicit formula. And it is expected that Nakamura's character induces isomorphism from between group 4 or group 6 and the symmetric product of Tate modules. So tensor with GP1. And in fact, these isomorphism holds if the elliptic analog of three character is non-trivial. And if these elliptic three characters are non-trivial, then we moreover can check that this equality between dimensions holds up to degree, I think, 12. So, 12. So this, so, and so, and one another evidence is that, in fact, we can prove the generation portion of the conjecture, but we have to assume that the finiteness of the second heterocomology group, as in the previous slides, and the proof uses Hein Matsumoto's approach. So I am now writing on this subject. And so in particular, under this assumption on H2, we have these equalities. So, and also I have no time. So in brief summary, so the Galois action on the fundamental group of one functional elliptic curves has very rich structures, which are analogous to the genus zero case, the P of minus 3 points case. And if we assume the linear Hauss conjecture, so we can describe the fixed field explicitly in field theoretic terms under some assumption on P. So that's all. So thank you very much.
Thank you for that wonderful talk.